we're going to talk about why we use the potentials, that is the scalar potential, otherwise known as the electrostatic potential, and the vector potential, to solve the general electromagnetism problem which we've encountered in thinking about the emission of radiation. Let's start by recalling where we've got to. So we have Maxwell's equations, which we're going to write as div E is equal to rho over epsilon naught, div B is equal to 0, our favourite monopole free equation, Faraday's law, curl of E plus dB by dt is equal to 0, and you'll notice that I've written that with the waves on the left hand side. I'm just going to shift that so that it's clearer that B is a vector, and then the Ampere-Maxwell law, curl of B minus epsilon naught mu naught dE by dt is equal to mu naught J. And you might well say, why can't we use these equations? Why can't we solve for E and B? Well, you can make full equations for E and B using the sources, which are now going to be time and position dependent. Let's see where we get to. So we'll start by taking the curl of Faraday's law. As we have done before. And what we find is the following. We have the curl of E plus, I'm now going to change the order of the differentiation, d by dt of curl B is equal to 0. We're going to expand out the curl of the curl, and we'll get the gradient of div E minus del squared E, that's the curl of the curl, and then I'm going to substitute in the Ampere-Maxwell equation, so we're going to have plus d by dt of mu naught J plus epsilon naught mu naught dE by dt is equal to 0. So far so good. This should all be fairly familiar. But now let's notice one thing. So we're going to note that the divergence of E we're going to keep as rho over epsilon naught. So when we expand out, then what we're going to get is the following. We're going to expand and we're going to rearrange it a little bit. So we have a minus del squared E. That's just keeping this term here, moving down to here. We're going to take the d by dt of this epsilon naught d mu naught dE by dt here, and we're going to turn epsilon naught mu naught into 1 over c squared. So we're going to have a d2E by dt squared. That's because we've got one d by dt and another d by dt. And now we're going to shift the source terms to the other side, and that's going to equal minus mu naught dj by dt minus the gradient of rho over epsilon naught. So we'll just multiply through by minus 1, and we're going to factor the epsilon naught into a bracket outside the right hand side. So the final result is as follows: del squared of E minus 1 over c squared d2E by dt squared, that's our familiar wave equation on the left hand side, is equal to minus 1 over epsilon naught into minus grad rho minus 1 over c squared, that's just epsilon naught mu naught, dj by dt. Now that's a rather complex equation to solve. The source terms on the right hand side in particular are complex. We're mixing in both current densities and charge densities. What happens if we do the same for B? Well, if we start by taking the curl of the Ampere-Maxwell equation, then we get the following. We get the curl of B minus mu naught epsilon naught, excuse me, missed that one, d by dt of curl of E, and again I've changed the order of the differentiation, is equal to mu naught curl of J. If I expand out the curl of B and recall that div B is equal to 0, then we get minus del squared B, that's just coming from here, and I'm going to substitute for it using Faraday's law, for curl of E with a minus dB by dt. So I'm actually going to need to shift everything down a bit. So I'm going to get a minus del squared B. I'm going to get a minus mu naught, a plus, excuse me, mu naught epsilon naught d2b by dt squared. That's because we've got a minus sign here and a minus sign here. They cancel to give us a plus, and that's going to equal mu naught curl of j. And if I just multiply it by minus 1 and convert the mu naught epsilon naught into a 1 over c squared, then I get del squared b minus 1 over c squared d2b by dt squared is equal to minus mu naught curl of j. And again, that's really not a very pleasant equation to try and solve. It's complicated, and the curl of j is not going to be something that's very helpful. So this is why we turn to the potentials. It's because the fields themselves become too complex. And what we're going to seek is a way to write the potentials in a decoupled form. So we want one equation for A, we want one equation for V or phi, and hopefully we'll only have one source term. So we're just going to recall how those potentials are written in this video, and then I'll go through how we develop this theory in the next couple of videos. So remember that we write B is equal to the curl of A, where A is the scalar potential, the vector potential, and that comes about because we know that the divergence of B is 0 and the divergence of a curl is identically naught. If we now turn to Faraday's law and curl of E plus dB by dt is equal to 0. If we substitute in for B, that tells us that the curl of E plus d by dt of the curl of A is equal to 0. And if we change the order of the differentials and pull the curl outside, then we can write that the curl of E plus dA by dt is equal to naught. And again, using the fact that the curl of a grad is always equal to 0, we can say that since this curl here is equal to 0, we can write this must be equal to a grad. Or we can certainly write it as being equal to a grad. Conventionally, we choose that gradient to be the gradient of the potential, the electric potential, and so we write E plus dA by dt is equal to minus grad of V. The minus sign is purely conventional. I have sometimes used phi for the potential. The two are equivalent, and notice that this phi has nothing to do with the magnetic flux, which is normally written with a capital phi, and therefore here, whoops, how did that happen? I'm just going to write this is the electric or scalar potential. That's probably a little bit clearer. So we can finally write that E is equal to minus the gradient of V minus dA by dt. So that's very familiar. So we define V, or sometimes phi, and if I write it as a phi and don't notice, please forgive me. This, as we said, is the scalar potential. And since E is written in terms of the gradient of phi, we are free to add any single number to it without changing E. In the same way, A we've defined as the vector potential, and we are free to add the gradient of a function, where f is any kind of scalar function, without changing the B field. There is a small restriction. If we change A by grad f, we must also change phi by minus df by dt in order to not change the electric field. I will show that in a little more detail in the next video. So, where have we got to? We started with Maxwell's equations for the fields. We are working in a situation where we have both current density and charge density, and both of them are going to be dependent on position and time. We then derived some equations here, one for the electric field. In fact, let me just outline that fellow in red. So here's the equation for the electric field, though I would never expect anyone to use that in anger. And the magnetic field we have an equation for here. And these are truly horrible equations. So what we're saying is we're going to try and develop simpler equations for the potentials, and we've reminded ourselves of the potentials and the fact that there is a certain amount of freedom with the potentials. In the next video, I'm going to talk about that freedom in setting the potentials, in setting a reference point. It's known formally as gauge invariance. And then in the video after that, I will derive decoupled equations for the scalar and the vector potentials. From there, we'll then have to think about how to solve those potentials, and we'll get to those videos as we get to them.